Hello guys, welcome to the second online lecture. Today we're gonna start talking about, we're gonna start talking about materials in the electric field. And mostly we're gonna talk about materials in the electrostatic field, to be more precise. So we're gonna talk how to handle the effect of having different kinds of materials in the electrostatic field. So the only way we included the effect of materials up to this point is through the permittivity constant epsilon. So remember when we talked about the we talked about the relationship between the electric field intensity and D, the flux density. So D equals epsilon naught E, right? So D is the field that does not depend on the material, because remember, E is proportional to 1 over epsilon naught. It has 1 over epsilon naught in whatever equation you have that expresses E. So when I multiply it by epsilon naught, I get D, which is a kind of field that does not, it's a flux density field that does not depend on the material. The idea here is that we can use this constant to describe properties of different materials. So different materials at the macro level will have different values for epsilon. For example, epsilon naught is for vacuum, right? And then you might have some other epsilon for some other kind of material, which we will talk about soon. Okay. We want to start with, though, talking about conductors. Okay, which have nothing to do with epsilon at this point. Conductors merely have something to do with charges and the freedom of movement in charges. So up to this point, when I was talking about any charge distribution, I was talking about a fixed charge distribution. Right? So I'm talking about the charge distribution that is fixed in space in certain locations. So I could have point charges fixed in space. I could have a volume charge distribution, a surface charge distribution, but all of this is fixed in space. And I calculate the field at any point due to those distributions that are fixed in space, right? We're still talking about statics. So we have no theory at this point to discuss what happens if the charges or the charge distributions move due to the interactions between them. So remember, we said that charges will create an electric field, and that electric field will cause a Coulomb force or any test charge, right? So we should expect the charge distributions to start moving around, and that gives us the theory of electrodynamics, which is a more complicated beast than what we are dealing with right now, and which we won't discuss yet. Okay, so we're still dealing with electrostatics, but even within electrostatics, we can still talk about how electrostatics interacts with what's called ideal conductors. Right? How electrostatics interact with ideal conductors at steady state. Right? So what happens is that if an electrostatic field interacts with an ideal conductor, the charges within the conductor move, but then they stop after a point. They reach some steady state. Right? The analogy here is if you have a skating rink, for example, skating rink. And the property of a skating rink, or whatever it's called, is that there is no friction, right? So if there's an object right in the middle, any tiny force, no matter how small, is gonna, due to Newton's law and of inertia, is gonna cause this object to move, no matter how small the force. The object will only stop. All objects will only stop when we reach the boundary, when we hit the boundary, right? Same thing with a ideal conductor. Ideal conductor is a type of material that does not oppose or does not show friction to any charge that exists within it. So any charge that exists within it is free to move as it wants. It's a free moving charge, right? That's what we call it, a free moving charge. Right? So what will happen if you have, like, let's say, two charges, and those charges are gonna two positive charges, let's say, and those two charges are gonna let me write that down properly. Right? Those two charges are gonna have a Coulomb force between them, right? Each one is gonna generate a field, and there's gonna be a Coulomb force between them. What will happen is, because the material shows no resistance to movement of charges, those charges are gonna accelerate and keep moving. They will only stop moving once they hit the boundary. Right? And the other thing that could happen is that if there's an external electric field, let's say, so we have a conductor and there's an external electric field acting on that conductor is typically going to be neutral, right? So here we discussed the conductor previously, where we kind of like put in two extra charges within the conductor. They feel the force between them, and they kind of keep moving until they hit the boundary, right? But we also, other than adding charges to a conductor, we could have an external field that's affecting the conductor, right? So what happens, because the conductor is neutral, it has equal number of positive and negative charges. This field is gonna, and those are free moving charges, this field is gonna disrupt those charges and cause them to redistribute, right? And they will redistribute in a way such that there's gonna be like a surface charge density on the boundary. All the charges are going to redistribute to the boundary, because that's where all charges are going to stop, or charge distributions are going to stop moving. Right? They can only exist on the boundary. If there's a charge distribution anywhere else in the internal insides of the conductor, it will have to keep moving until it hits the boundary. That's the key property of ideal conductors. Right? So, and that allows us to describe them and describe their behavior at steady state quite easily, right? Oh, by the way, when you have this external electric field that acts on a conductor and causes the charges to redistribute and causes some surface charge density to appear on the conductor, this kind of induced charge is called an induced charge within the conductor. Right? Because here we're not adding any extra charge to the conductor, we're inducing a charge in the conductor by separating the already existing positive and negative charge densities that exist within the conductor. Right? The conductor ultimately, I mean, this is all ideal, but in real life, the conductor does have an equal distribution of there is no conductor that has no charges in it whatsoever. Right? An ideal conductor will have an equal distribution of positive and negative charges that gets redistributed under the influence of an external field, because we know an ideal conductor, it consists of atoms, right? And electrons around those atoms. Right? We know nuclei and electrons. All right. So, having talked about this in general, let's talk about the qualitatively describe the general properties of conductors. All right. So yeah, their properties can be distilled into three basic properties. So the first one we already talked about, charge introduced into a conductor always moves towards the surface of said conductor. Right? Right? If we introduce a charge inside the conductor, uh, the charge always moves to the surface. Let's say if you rub uh, a glass tube, right, and then you make it touch a conductor, right, whatever, so there's positive charge here, right, it will get to the conductor and then it will redistribute towards the surface. Okay, that's property 1. Property 2, in steady state, charges distribute themselves on surface of conductor such that, right, so they will distribute themselves on the surface of the conductor such that three main things happen. Okay, three things happen. 1, 2. The first thing is that the electric field is 0 in interior. Right? That's the first thing that happens. The second thing that happens is that the tangent field ET is 0 at surface, right? And third thing that happens is that only field is the only field which exists is the normal field En at surface, right? So let me describe those three properties a bit in detail. Okay, so the first one is that in steady state, meaning after all the free charges have moved and went to the surface, stopped at the surface, right? In steady state, those three things will happen. The electric field will be 0 in the interior. Why is that true, by the way? Right? So we said we had a conductor. We either introduce charges within the conductor and they move to the surface, or we have an external field that gave us some induced charge distributions. Whatever happens, the charge distribution, it's going to be a surface charge distribution at the surface, at the boundary of the conductor. Right? So from Gauss's law, I could have a Gaussian surface here in the middle of the conductor. From Gauss's law, I know that all the charges are on the surface of the conductor. So I know from Gauss's law that there is no enclosed charge inside this Gaussian surface, right? Q enclosed is 0. So that tells me that the electric field times this Gaussian surface is going to be 0, right? From the symmetry, that tells me that the field needs to be 0. So E is 0 inside the conductor, always at steady state. Initially, there is some E that moves the charges, but once all the charges get to the boundary, the basic property of the conductor, ideal conductor, is that the electric field will always be 0 inside the conductor. Right? That's one. The other thing is that the tangent, what about the tangent field? Okay. right? So the tangent field is that at the surface of the conductor, any field in the tangent direction, ET, must be zero. There must not be a tangent component of the field at the surface of the conductor. Why not? What happens if there is a tangent component of the field on the surface of the conductor? Well, what happens is that this causes the charge distribution at the surface to flow, to move on the surface. So you reach the boundary, but you're still moving at the boundary. Yes, it's like reaching the end of the skating and then skating, by the fence or around the fence, right? But that's not steady state. If there's still charge movement, that's not steady state. At charge movement, everything has to have stopped, and everything will stop only if there's no electric field. So that's why the tangential component of the field has to be zero, right? The only field that can exist is the field that pushes the charge onto the boundary, right? So the only field that exists is the field that's normal to the boundary. And this field that's normal to the boundary can be positive or negative. It can be pushing out, it could be pushing in. Right? It's going to be pushing out if there's like a positive charge distribution. It's going to be pushing in if there's a negative charge distribution at that point of the boundary. Okay. Yeah, so those are the three basic facts explained. Right? The electric field is zero in the middle of the conductor. The tangential electric field has to be zero, and then the only component of the electric field that exists that has any value is going to be the normal component. And the third property is that also the volume charge density inside conductor is zero. Right? We said why this is true using Gauss's law here. Right? We could have explained it in a different way and said, hey, if there is any charge density inside the conductor, those charge densities are gonna have a Coulomb force between them, and they'll have to separate and go to the boundary. So at steady state, none should exist, because if any exists, we're still in movement. We still have opposing charges that that are moving towards the boundary. Right? So that's another way of stating the same fact. Okay, so it's a fact about so it's a fact. The three facts are facts about the existence of surface charges, surface charge distributions. The second facts are facts about the electric field within the conductor and on the boundary of the conductor. And then the third property is about the volume charge density inside the conductor, which turns out to be zero. Right? I mean, the fact about the normal field is intriguing. This tells us that, hey, if I have any conductor and I have any external field in space, those field lines will always arrive at the conductor at an angle of 90 degrees. They'll always be normal to the conductor, so the field lines might do this. Right? If you drew field lines for a hypothetical scenario where there's an external field E, right, you'll find that the field lines are always normal to the conductor, always at an angle of 90 degrees. It's as if the conductor bunches the fields towards it and at an angle of 90 degrees. Okay, how do we relate the field, the normal field with the charge distribution at the surface? Well, we use Gauss's law, right? So let's zoom in. So we have this conductor. Let's zoom in to a small portion, small area on the surface. So it looks like this, right? So, and we said that there is only a normal component of the field, right? So let me take the normal component of the field just above the surface, so that this component of the field, right, just above the surface, this normal component of the field, because we are zooming in so much, is going to be, about the same as the field that exists on the surface, right? And we can use Gauss's law. I can take a Gaussian surface, and I can take it, extend it underneath the surface, right? So E inside the conductor is 0, so this is conductor. So from Gauss's law, En times S, the surface area here is S, equals rho SS over epsilon naught. So that tells me that En, the normal component of the electric field, which is the only component that has any value on the surface of the conductor, is going to be rho S over epsilon naught, volt per meter. So this is the relationship between the field and the surface charge density on the surface of a conductor. It's simple. It's just take the field multiplied by epsilon naught, you get the charge density, surface charge density, get the charge density divided by epsilon naught, you get the field. Taking the epsilon out by looking at the flux density, I get dN equals rho S. Right? All right. So pretty simple stuff up to this point. It's conductors have very nice properties. Like if you think about it, that's the point of why conductors are used in transmission lines, right? If you think about it, what's a transmission line? So we have the generator, right? What does a generator do? Generator is a machine that takes fuel, right? And through something called electromagnetic induction, it generates a voltage. That's what it does. It generates between two wires. So let's look at just a single phase of this machine. Typically, a machine would have 3 phases coming out of it. But let's look at single phase. So typically, out of the machine, you will have 2 wires extending out, and this is gonna generate an electric field. So there's gonna be an electric field between those 2 power. Because the machine, as it's rotating, generates a potential difference, a voltage difference, and that means there is an electric field coming out from one terminal and reaching the other terminal. So this is local, right? But we want to transmit this force geographically to a faraway location. So how do we do that? We do that by connecting transmission lines. Transmission lines are conductors, or as ideal conductors, or as close to ideal conductors as possible. They're not actually ideal conductors, but we could consider them to be close, right? So those transmission lines, what they do is that they take this field and they move it to the other side, right? But because they are conductors, the field inside the conductor itself will be 0. Right? So there will be minimal losses on the transition. We'll talk about that later, but that is the nice property of conductors. That's why it's nice that the field inside them is going to be 0 once things have settled. Okay, so I don't want to dwell on this too much, but just giving you a heads up. Okay, we'll discuss this later. I want to go now through examples. So in the textbook, there are a bunch of good examples. So let's start with example 4.13. Okay. So what does it say? It says, hey, you have a certain conductor, and then you know I'm giving you the normal field, telling you this is a known. The normal field at any point on the surface is 100 volts per meter. And the conductor is in free space, meaning that the permittivity is epsilon naught. So part A asks, what is Rho S. What is the surface charge density? Well, we derived that, right? Rho S is just epsilon naught times En. Oops. So rho S equals epsilon naught times En. Pretty simple. That equals 100 times 8.854 times 10 to the power minus 12. That's 8.854 times 10 to the minus 10 coulomb per meter squared. Right? So that's part A, pretty simple. Part B. What is E, the electric field intensity, and V, the potential energy? Remember, we discussed the potential energy last week. Inside the conductor, if the potential energy at the surface is 10 volts. Right. So remember when we talked about potential energy, we said it's just a scalar field in space, right, where it relates to the electric field by the gradient. Right. So this is the differential form, and then E. And then the V between 2 points is just the integral from A to B E dl. Right. So we know that the potential energy is something that we can always add a constant to, right? And it won't change, right? If I have a scalar field and I just add a constant to it, the gradient of the constant is going to be 0, right? So the potential is something you can always add a constant to, and it will never vary, right? And when you look at the integral form of the potential, that's why we only look at potential difference. That's what matters. Potential difference is what matters. Right? So typically, and we did that when we looked at the potential of the point charge, we just assumed C2 equals 0, meaning we just assumed that the potential at infinity for a point charge is 0. So a good starting point in many problems is to assume that the potential at infinity equals 0 at a very large distance. It's only when we get charges closer and closer to a charge distribution does the potential deviate away from 0. Okay. The question is now, what is, we haven't discussed this yet, the question is, what is the potential, if you have an electric intensity field and you have a scalar potential field, what is the potential inside the conductor? Right? I mean, the result that we will discover is that the potential inside the conductor is going to be the same as the potential on the surface. And the potential should be equal on the surface. Any point on the surface. I'll show you why. Okay. So, but first off, let's start with E internal. E internal inside the conductor, this is internal, is 0, of course. We know that. We don't need to calculate that. This is a property of an ideal conductor. Okay. What about the potential? Well, so we have the conductor. What's the so I know the potential on the surface, right? And then I said that the potential at any point on the surface is the same. Vs is the same at any point of the surface. Why is that true, by the way? Right? If I move the electric field, why? I'll tell you why. Because the electric field, let's say I have Vs1 and Vs2 on the surface. The electric field between Vs1 to Vs2 is just minus E dl, right, from S1 to S2, right? So that's Vs2 minus Vs1, right? So I'm moving on the surface, but the electric field is always normal to my movement. It's always at a 90 degrees to my path along the surface. So this will always be 0, right? So that means Vs2 will always equal Vs1. So the surface potential is going to be the same anywhere on the surface, right? What about the potential on the interior? Well, again, I'm gonna take the potential on the surface. We said if we know the potential of this on the surface at one point, it will be the same at any point on the surface. What about somewhere in the interior? Let's say on the surface I'm at point A, interior I'm at point B. What's V interior at point B? Well, again, let me take Vn minus Vs equals right? So A to B E dl. Now I said the potential in the interior is zero, right? The electric field intensity, sorry, in the interior is zero. So this whole thing is zero. So that tells me that the interior potential equals the surface potential. So V interior is 10 volts. Okay. So this is another basic property of conductors in general. We could have stated it, but it's not, I mean, we could derive it from what we already know. But the basic property is that every point in a conductor has the same potential, has the same voltage. Right? That is the basic property. Another way of describing it that harkens back to what you learned in circuits is that the conductor is something with a zero voltage drop, right? An ideal conductor, a short circuit. Okay. All right, so I'll go now to the next example. Example 4.14. My surface is, the fan is running at full steam. I hope the sound is not being recorded, or I'll find out, I guess. Okay, so example 4.14. So this example is about a point charge Q and a conducting shell. So there's a sphere around Q. Right. When I say a sphere is always the shell of a ball, right? Like an eggshell is if this was a ball, it would be like a sphere. Sometimes some people sometimes confuse the two. So when you tell them a sphere, they think a ball. Okay. So this is a shell of a conductor. So this is a conductor. This is empty space here, and this is empty space, and this is a conductor. Right? So it's like a shell that has a certain thickness around the point charge. So the inner shell is at a distance A, the outer shell is at a distance B. The question is the following. What is E and V everywhere in space? Right, that's what we want to find. And B, what are the surface charge densities on the inner and outer surfaces of conducting shell? Meaning, what are the charge densities on this surface? So this is a conductor with two surfaces, separate surfaces. So what are the charge densities here? Let's call it rho SA. And what are the charge densities on, what is the charge density on this surface? Let's call it rho SB. Okay, so let's start. So we can apply Gauss's law, right? It's a symmetrical problem. So for r less than, now I'm using spherical coordinates due to the spherical symmetry. So for r less than a, Gauss's law states that the field there, the radial field, right, is going to be E times the right? So this is actually, let me draw my Gaussian surface. This is my Gaussian surface. It's a sphere here. And then my outer Gaussian surface is the sphere outside the conducting shell. Okay? So E times the surface area of the Gaussian surface sphere, 4 pi r squared, equals Q over epsilon naught. So that tells me E equals Q over 4 pi epsilon naught r squared. Pretty standard results for a point charge. Put back the vectorial aspect. So this becomes r hat Q over 4 pi epsilon naught r squared. This is for r less than or equal a. Okay, so that's a fact. What about r larger than or equal b? Let me simplify things. Let me say r less than a. I don't want to worry about the surface at this point. Okay, now here's the key insight for this problem. See, because of this charge Q generates electrostatic field, and that field induces charges in the conductor, meaning some charge distributions in the conductor start moving around and go to the surface. But overall, the total charge inside the conductor is zero. All that happened due to the existence of Q is that the charge redistributed itself inside the conductor. Right? But overall, the total charge is zero. The conductor overall is neutral. Meaning if I apply Gauss's law outside B, the total charge in the conductor remains zero, although it's redistributed so that some charges exist on the surfaces. The total charge is still zero. The only charge that remains is Q. So E will have the same form. If R larger than B, E will still be Q over 4 pi epsilon naught R squared. I'll just stick to the magnitude. Okay. So when I plot E, and the third property is, the third thing we can say is that E, of course, inside the conductor is zero. Right? We know that. So if I plot E with respect to R, so I have A and B. When I am less than A, I have the regular inverse squared law, and then the E goes to zero inside the conductor, remains at zero, and then goes up, and then goes down again. This is what E looks like. So the fact is that E equals zero inside conductor. Okay. We still have to do the potential energy. Okay, what is the potential energy? Okay, again, let's assume the potential energy at infinity is zero. Right? We can always assume that because we can always add constants to the potential energy. We just, select the potential energy such that scalar field such that at infinity is zero. Okay. So when going from infinity to the surface to B, VB is going to be minus. So we're going from infinity to B, E dot dl. We're trying to find the potential energy at B, right? So that's going to be, let's do this calculation. That's going to be minus infinity to B of R hat Q over 4 pi epsilon naught R squared dot R hat dr. That's going to equal minus to B. Let me take the constants out. That's going to be Q over 4 pi epsilon naught integral from minus infinity to B 1 over R squared dr. I know how to do this integral, easy. So that's going to be, let me put the minus in. So that's going to be Q over 4 pi epsilon naught. This is just 1 over r, right? When I differentiate 1 over r, I get minus 1 over r squared. This goes from minus infinity to b. 1 over infinity is 0, so that gives me Q over 4 pi epsilon naught b. We got this result right before when we talked about potential energy. And looks like a potential energy for a point charge, really. Okay. So this is the potential energy up to the at the surface, right? In general, the potential energy at R, where R is larger than B, is going to be Q over 4 pi epsilon naught R. We calculated this result in a previous lecture. Okay. And what did we say about potential inside the conductor? So inside conductor, right? So the potential at the surface of the conductor is going to be this. We said that the potential inside the conductor will be the same at the surface. Effectively, it will be the same at every point in the conductor, right? So anywhere in the conductor, Vx equals Vb, where x is some value larger than A less than B. Let me, instead of x, let me say R, because this is spherical coordinates, okay? Another way of describing it is saying that a conductor is an equipotential volume, right? Potential energy does not vary. Okay. What about for R less than A? Right. Same thing. VR is going to be, we're going to go from minus infinity to R, E dot dl. There's a minus sign here. So we can divide this motion from minus infinity to R to minus infinity to B, right? Q dr over 4 pi epsilon naught r squared, minus, then we go from B to A, 0. We said the electric field is 0 there inside the shell, then minus from A to R. R here lies inside the shell, right? R now goes to some point here inside the shell, right? And this is Q dr over 4 pi epsilon naught r squared. So we already calculated this part, right? This part turns out to be Q over 4 pi epsilon naught B. This part is 0. And then the final part is going to be plus Q over 4 pi epsilon naught. I took Q over 4 pi epsilon naught out, the constant. And then I integrate minus 1 over r squared. I end up with 1 over r. And then I put in the limits of the integral. So this becomes 1 over r minus 1 over a. So I end up with the general VR being let's see, I end up with the general VR being Q over 4 pi epsilon naught 1 over B minus 1 over A plus 1 over R. This is true for R less than or equal B. Right? So let's plot this. So let me plot V versus R. So we did, so for up to R, for R larger than B, this is the formula. It's not an inverse square, it's just an inverse. So it looks something like this until we hit B or A. Okay, B is the larger value. So we hit B first. Oops. And then it remains constant inside the conductor shell. And then at A, it starts going down again. Okay. Let me double check if I did the other figure right. Ah, okay, so oh, sorry. I think, yeah, I think I it's still A, B. As I'm going from the middle to infinity, I'm hitting A first and then B. Okay. So this is what it looks like. Notice the difference between the electric field and the potential energy. Okay. The final part is calculating the surface charge densities inside the conductor. Okay, and here we use Gauss's law. So let me redraw this. So I have Q and I have A, and this is the conductor shell. The first question I need to ask myself is what is the charge density at in the inner surface, right? I can put my Gaussian surface in the middle of the conductor like this, right? And I know that using Gauss's law, E is 0, right? Inside the conductor, so this is 0. But this also needs to equal Q enclosed over epsilon naught, right? So 0 has to equal, what's the enclosed charge here? The enclosed charge here is going to be the surface charge density and the Q. So the enclosed charge is going to be Q over epsilon naught, and the total charge on the surface is going to be rho SA. This is rho SA, by the way. Rho SA 4 pi A squared, the surface area of the inner sphere, over epsilon naught. I can do some algebra, manipulate this. So epsilon cancels with epsilon. I end up with rho SA equals minus Q over 4 pi A squared Coulomb per meter squared. Okay, how do I find rho SB? Well, I use the fact that total charge in conductor is 0. Okay. So this tells me that the charge on the inner surface plus the charge on the outer surface equals 0. So that tells me that rho SB 4 pi B squared, this is the charge on the outer surface, right, plus the charge on the inner surface, rho SA 4 pi A squared equals 0. So that tells me that rho SB equals what? Well, 4 pi cancels with 4 pi, right? So that tells me that rho SB equals minus rho SA A squared over B squared. But we already calculated rho SA here, right? It's minus Q over 4 pi A squared. So this becomes Q over 4 pi A squared over B squared. A squared cancels, and we end up with rho SB equals Q over 4 pi B squared. So we got those results. Okay, so this concludes our discussion of conductors at this point. We're going to continue our discussions on materials in the electrostatic field by starting talking about dielectric materials. Okay, so this is what we're going to dielectric materials. Okay. All right, and we're going to start talking about this in the next lecture. Alright, thank you guys, and again I'm gonna post this on the discussion thread. If you have any questions, you can post them on the thread itself. But please do that quickly, like within a couple of days, because after a couple of days I'm gonna close the thread so that so that I can open a new one. All right, have a good day. Bye.